Good morning, everybody. Happy Tuesday. Happy first day of the next 9 weeks. Okay, while we're waiting for everybody to come in, if you would go, I know most of you have finished your microscope activity. So if you would, and again, like some folks noticed that it had given a 0 maybe already. Don't worry about that. I don't know. I didn't even have access to grading those. So this will, like I said, was not included in the last 9 week. It'll be the first assignment in this 9 weeks. So have no fear about, you won't get a 0. No zeros, no zeros. It wasn't due until today, and I probably will need to change that due date to later on in the week, even though we don't have classes and later on in the week, just so that it's not a 0. All right, so if you would read over this, like I said, while we're waiting for everybody to come in, because like only half the class is here right now. But we're in Canvas looking at the microscope module. A lot of vocabulary, a lot of vocabulary. Like if you did the activity, so there's a lot of parts and a lot of things, but we're going to focus on now how the microscope is helpful for forensics. All right. All right, good morning, good morning. So if you're just coming in, we're looking at the overview for the microscope in Canvas, and then we're going to move on to how the microscope is used, and we're focusing on how it's used in forensics. You all did the microscope activity, which was a basic, what is a microscope? What are all the parts of the microscope? So needless to say, we won't be doing that with this. We're going to, like I said, focus on how the microscope is used in forensics. Why is it important? All right, I'm going to stop sharing for a minute, but I'll be right back. So again, if you're just read the first two sections. Still waiting for quite a few people to come to class. They're late, but we're gonna wait so I don't have to repeat too much. And again, if you have not turned in your microscope activity, please turn that in because it is due today. All right, good morning, good morning. We're in Canvas. We're reading the first two sections of the microscope unit. All right, good morning again. If you just came in, we are reading the first two sections of the microscope lesson. Okay. I think everybody else is just late. All right, so we're going to go ahead and get started with the video, and then we'll come back. So again, our focus is not just on the activity you did was on parts of the microscope, and that's wonderful, but now we want to know, how is that important in forensics?
Tool that we're going to use quite a bit this year. So the first thing you should know is that in most science classrooms, we use a light microscope to magnify objects. And as its name suggests, it uses light to allow us to see an image. Now, we also call these microscopes compound light microscopes because it uses two lenses. And I'll explain more what that means in just a second. So one of the lenses is going to be called the eyepiece and the other is called the objective lens. But these two lenses work together to help magnify the object, which is the purpose of using the microscope. We want to magnify objects that are otherwise too small to see with the naked eye. So in a nutshell, when we use compound light microscopes, we are going to pass light through our sample, which is known as the specimen, and it's going to create a magnified image. This image is going to pass through the objective lens as well. So it's going to pass through the objective lens first and then the eyepiece, and the eyepiece is what we actually look into to see our specimen magnified. Again, the two lenses work together to magnify the image so that it appears larger to the naked eye. Now, there are several parts to a microscope. If you've ever used a microscope before, you know there's a lot of different things going on the microscope. So that is our goal today, to learn all the different parts of the microscope, and then we'll have some time where we actually use and manipulate these different parts. I know it's hard sometimes when you're just listening to a lesson or watching a lesson, and this is really better if you can just kind of dive in and practice using the microscope, but we've got to learn the parts first. So that's what we're doing today, is learning all the different parts of the microscope. Now I have a diagram here, but not all microscopes are made the same way. So just keep in mind the coarse adjustment knob on this image might be in a different place than the actual microscope that you use in the classroom. Same thing. Sometimes the objective lenses are a little different. Sometimes these knobs are in different locations. So the diagram is just used for us to learn the parts, but the learning will actually take place when you start manipulating these parts. All right, so let's start with the eyepiece, which is generally at the top of your microscope. This is the part that you look into to view the specimen. Now, if you have just a basic microscope, you might only have one eyepiece, but in some fancier microscopes, you might actually have two eyepieces. Sometimes the eyepiece is known as the ocular lens, so you'll see both of those terms used interchangeably. Just make sure you know the eyepiece and the ocular lens, they mean the same thing. So the eyepiece is just a place to actually view the specimen with your eye. Now, right below the eyepiece, you have this part called the body tube. And the purpose of the body tube is just to provide some distance between the objective lenses, which are down here, and the eyepiece, which is at the top. Right below the body tube, you have what's called the revolving nose piece, and as the name suggests, it rotates, it revolves. You can turn it and rotate it to select the objective lens that you want to use. My microscopes have 3 objective lenses, but sometimes microscopes will even have 4 objective lenses. So depending on what you use in the classroom, yours might be a little different than mine, but mine use 3 objective lenses. I have 3 options for viewing my specimens. I can view my specimen on low power objective, which is my shortest objective lens, and it's going to magnify the specimen 4 times its original size. I also have a second option called a medium power objective. It's going to magnify my object 10 times the original size. And then the high power objective lens is always going to be your longest objective lens. It magnifies the greatest. So for my microscope, it magnifies 40 times the original size. And this lens is going to be closest to the specimen of the three. So if you choose the high objective lens, there's some precautions that you have to use that we'll talk about in a few slides over. All right, right below the objective lenses, you have this black or gray piece on the microscope that's called the stage. The stage holds the slide, the microscope slide. We talked about the microscope slide in a previous lesson where we talked about lab safety or lab equipment. So we know what that is. So the stage holds the microscope slide, which generally holds the specimen, and light will pass through that specimen, through that microscope slide, and up into the objective lens. Right below the stage, you have something called the diaphragm, and the diaphragm turns and will allow us to adjust the amount of light that passes through this specimen. So it just allows us to adjust the level of light that comes through what's called the condenser lens, and sometimes specimens require more light to be seen than others, and so the diaphragm just helps us adjust that light. Now, on the side of the microscope, you have what's called the arm, and at the bottom, the microscope sits on what's called the base. Both of these parts of the microscope are support systems. It just allows us to hold the microscope securely and just provides support. Going back to the stage will often have stage clips on the top of it, and these stage clips help to clamp the slide in place so that we can view the specimen without the specimen or the slide moving around. The light source is below the diaphragm, so at the very base of the microscope, you typically have a light source, and when you turn on the microscope, light projects out from the light source up to the diaphragm. Again, that diaphragm regulates how much light can pass through the specimen, but the light source is just usually at the bottom, and it projects light. All right, on the sides of the microscope, you have a few knobs. One is called the fine adjustment knob, and the other is called the coarse adjustment knob. Now, the coarse adjustment knob is usually, not all the time, but usually your larger of the two, and then your fine adjustment knob usually is the smaller of the two. The fine adjustment knob helps to fine tune the focus. So when you get your specimen in view, and sometimes it's a little cloudy, you can turn that fine adjustment knob just a tad, and it will help to crisp the image. It just provides a little more adjustment to the focus. You can use the fine adjustment knob with all of your objective lenses. So you can use it with low, medium, or high power objective. Now, the coarse adjustment knob is going to actually move the stage up and down vertically. And because it moves the stage up and down towards those objective lenses, it is very important that you only use the coarse adjustment knob with the low and medium power objective lenses. So you should never use the coarse adjustment knob with your high power objective lens. Remember, your high power objective lens is your longer lens. It's very close to the stage, and so if you turn that coarse adjustment knob and the stage moves up, you could crack the objective lens. And these microscopes are sometimes very expensive. We don't want to do that. All right, so how are we going to calculate magnification? So if we're using a compound light microscope, remember we're using two sources of magnification or two lenses that magnify. And so occasionally you'll need to know the total magnification of the specimen that you're looking at. And so the way you're going to do this is just simply by multiplying the magnification of your objective lens by the magnification of your eyepiece. So if I am looking at my specimen under the low power objective lens, which has a magnification of 4x, and I'm looking at it through my eyepiece, then what I'm going to see is a total magnification of 40x. 400x. That means 40 times the original size of the specimen. If I choose the medium power objective lens and I look at the specimen through the eyepiece, then I'm getting a total magnification of 100 times the original size, so 100x. And then if I use the high power objective lens with the eyepiece, I'm getting a total magnification of 400 times the original size, so 400x.
A man who works hard sweats hard.
Old Spice swagger fights sweat. So Coach thought.
All right, just some things to remember. So we're going to go through sort of some rules for when you're using the microscope.
Okay, I'm going to pause it there. Unfortunately, you all are not in the classroom, so you won't have to worry about all of these things. It would be nice, but we're going to skip this. And that was just a brief review. Hopefully, like I said, you did your worksheet and you did the activity that was on the virtual site, which had you go through and actually use the microscope and label the microscope, use the microscope. So that was just a review. Like I said, I think most people who are coming today are here, so we will move back here. All right, so that was a basic microscope that she was talking about, the one at the top, the compound microscope. But the microscopes that are used in forensics are usually not the first two, but the other four, because they are specialized for looking at special fibers, things that, and again, most of the things that they're looking for are microscopic in size, and our objective is to find evidence so that we can solve the case, okay? And again, the part that's important is you have to be careful in your evaluation, remain objective. They must not make assumptions, but most importantly, you want to make sure that with what you find under the microscope and your conclusion about what you find under the microscope is accurate so that it is admissible in court. Remember, our whole objective is we are trying to have evidence to solve a crime. All righty, so we've gone through that. So we're kind of go through this little module kind of quickly because most of what is here, let's go. So do read that. Do read that. All right, I tell you what, take the next few minutes to read. So now I'm on comparison. So you should be at least there because we've already watched the video on compound microscope. So look at comparison microscope. Always know who first used Calvin Goddard. No names of people who are first. And then we come to the stereo microscope. And again, be aware of the inventor of the stereo microscope. All right, that brings us here. So go ahead and read up to this point. I'm going to do attendance. Be right back. And then we'll look at this one together. If you just came in, we're in Canvas on the microscope module, and we're reading. All right, get all the way up to polarizing microscope, and we'll do that one together. Come to class. Okay. All right, you might have heard polarization. Some of you might have sunglasses that have a polarizing lens. So this kind of explains what polarizing does as far as light being able to pass through.
In the last couple of videos, we talked about reflection. And that's just the idea of the light rays bouncing off of a surface. And if the surface is smooth, the incident angle is going to be the same thing as the reflected angle. We saw that before, and those angles are measured relative to a perpendicular. So that angle right there is going to be the same as that angle right there. That's essentially what we learned in the last couple of videos. What we want to cover in this video is
I'm gonna pause it right there. Hopefully, you remember from physicals that you covered this in physical science when you were in middle school about light bouncing off a surface. And what we see is reflected light. So it always has to hit a surface and then it bounces back to your eye. And it bounces at a certain angle. So that's what he's talking about.
Is when the light actually doesn't just bounce off of a surface, but starts going through a different medium. So in this situation, we will be dealing with refraction. Refraction. Refraction, you still have the light coming in to the interface between the two surfaces. So let's say, that's the perpendicular right there. Actually, let me continue the perpendicular all the way down like that. And let's say we have the incident light ray coming in at some angle theta 1, just like that. What will happen? And so let's say that this up here, this is a vacuum. Light travels the fastest in a vacuum. In a vacuum, there's nothing there, no air, no water, no nothing. That's where the light travels the fastest. And let's say that this medium down here, I don't know, let's say it's water. Let's say that this is water. All of this is all water over here. This was all a vacuum right up here. So what will happen? And actually, that's kind of an unrealistic. Well, just for the sake of argument, let's just say that we have water going right up against a vacuum. This isn't something that you would normally just see in nature, but let's just think about it a little bit. Normally, the water, since there's no pressure, it would evaporate and all of the rest. But for the sake of argument, let's just say that this is a medium where light will travel slower. What you're going to have is this ray is actually going to switch direction. It's actually going to bend. Instead of continuing to going in that same direction, it's going to bend a little bit. It's going to go down in that direction, just like that. And this angle right here, theta 2, is the refraction. That's the refraction angle. Refraction angle. Or angle of refraction. This is the incident angle or angle of incidence, and this is the refraction angle, once again, against that perpendicular. And before I give you the actual equation of how these two things relate and how they're related to the speed of light in these two media, and just remember, once again, you're never going to have vacuum against water. The water would evaporate because there's no pressure on it and all of that type of thing. But just to, before I go into the math of actually how to figure out these angles relative to the velocities of light in the different media, I want to give you an intuitive understanding of not why it bends, because I'm not telling you actually how light works. This is really more of an observed property. And light, as we'll learn as we do more and more videos about it, it can get pretty confusing. Sometimes you want to treat it as a ray, sometimes you want to treat it as a wave, sometimes you want to treat it as a photon. But when you think about refraction, I actually like to think of it as kind of a bit of a vehicle. And to imagine that, let's imagine that I had a car. So let me draw car. So we're looking at the top of the car. So this is the passenger compartment, and it has 4 wheels on the car. And we're looking at it from above. And let's say it's traveling on a road. It's traveling on a road. On a road, the tires can get good traction. The car can move pretty efficiently. And it's about to reach an interface. It's about to reach an interface where the road ends, and it will have to travel. It will have to travel on mud. It will have to travel on mud. Now, on mud, obviously, a tire's traction will not be as good. The car will not be able to travel as fast. So what's going to happen? Assuming that the steering wheel isn't telling it to turn or anything, the car would just go straight in this direction. But what happens right when, which wheels are going to reach the mud first? Well, this wheel right here is going to reach the mud first. So what's going to happen? There's going to be some point in time where the car is right over here. Where it's right over here. Where these wheels are still on the road. This wheel is in the mud, and that wheel is about to reach the mud. Now, in this situation, what would the car do? What would the car do? And assuming that the engine is revving and the wheels are turning at the exact same speed through at this the entire point of this the entire time of the simulation. Well, all of a sudden, as soon as this wheel hits the medium, it's going to slow down. This is going to slow down, but these guys are still on the road, so they're still going to be faster. So the right side of the car is going to move faster than the left side of the car. So what's that going to happen? I mean, this is you see this all the time. If the right side of you is moving faster than the left side of you, you're going to turn, and that's exactly what's going to happen to the car. The car is going to turn. It's going to turn in that direction. And so once it gets to the medium, it'll now travel. It'll now turn from the point of view from the car, turning to the right. But it'll now travel in this direction. It will be turned when it gets to that interface. Now, obviously light doesn't have wheels and it doesn't deal with mud, but it's the same general idea. When I'm traveling from a faster medium to a slower medium, you can kind of imagine the wheels on that light on this side of it, closer to the vertical, hit the medium first, slow down so the light turns to the right. If you're going the other way, if I had light coming out of the slow medium, so let's imagine it this way. Let's have light coming out of the slow medium, and if we use the car analogy, in this situation, the left side of the car is going to, so if the car is right over here, the left side of the car is going to come out first, so it's going to move faster now. So the car is going to turn to the right, just like that. So hopefully this gives you a gut sense of just how to figure out which direction the light's going to bend if you just wanted an intuitive sense. And to get to the next level, there's actually something called Snell's law. Snell's law. And all this is saying is that this angle, so let me write it down here. So let's say that this velocity right here is velocity 2. This velocity up here was velocity 1, going back to the original. Actually, let me draw another diagram just to clean it up. And also, that vacuum water interface example, I'm not enjoying it just because it's a very unnatural interface to actually have in nature. So maybe it's vacuum and glass. That's something that actually would exist. So let's say we're doing that. So this isn't water, this is glass. So let me redraw it. And I'll draw the angles bigger. So let me draw perpendicular. And so I have our incident ray. So in the vacuum, it's traveling at v1. And in the case of a vacuum, it's actually going at the speed of light, or speed of light in a vacuum, which is c, or 300,000 kilometers per second, or 300 million meters per second. Let me write that. So c is the speed of light in a vacuum, and that is equal to 300. It's not exactly 300. I'm not going to significant digits. It's true to 3 significant digits. 300 million meters per second. This is light in a vacuum. Light in vacuum. And I don't mean the thing that you use to clean your carpet with. I mean an area of space that has nothing in it. No air, no gas, no molecules, nothing in it. That is a pure vacuum, and that's how fast light will travel. Now it's traveling really fast there. And let's say that this is, and this applies to any two medium, but let's say it gets to glass here, and in glass it travels slower. And we know, for example, this side of the car is going to get to the slow medium first, so it's going to turn in this direction. So it's going to go like this. And we call this v2. And maybe I'll draw it. If you wanted to view these as vectors, maybe I should draw it as a smaller vector. v2, just like that. And the angle of incidence is theta 1, and the angle of refraction is theta 2. And Snell's law just tells us that the ratio between v2 and the sine, remember SOHCAHTOA, basic trig function, and the sine of the angle of refraction is going to be equal to the ratio of v1 and the angle of incidence, and the sine of the angle of incidence. Sine of theta 1. Now, if this looks confusing at all, we're going to apply it a bunch in the next couple of videos. But I want to show you also that there's many, many ways to view Snell's law. You may or may not be familiar with the idea of an index of refraction. So let me write that down. Index of refraction. Index, or refraction index. And it's defined for any material. There's an index of refraction for a vacuum, for air, for water, for any material that people have measured it for, and they usually specify it as n, and it is defined as the speed of light in a vacuum, that's c divided by the velocity of light in that medium. So in our example right here, we could rewrite this. In terms of index of refraction. Let me do that actually, just because that's sometimes a more typical way of viewing Snell's law. So I could solve for v here. One thing I can do is just, if n is equal to c divided by v, then v is going to be equal to c divided by n. And I can multiply both sides by v if you don't see how I got there. The intermediary step is You multiply both sides times v, you get v times n is equal to c, and then you divide both sides by n, you get v is equal to c over n. So I can rewrite Snell's law over here as instead of having v2 there, I could write instead of writing v2 there, I could write the speed of light. The
I'm going
speed
to
of
fast
is
forward
really just
this.
tells you it's just the ratio of the speed of light to indices for different materials. It's obviously 1 for a vacuum, because for a vacuum you have the refraction index is going to be c divided by the speed of light in that material. Well, in a vacuum it's traveling at c. So it's going to be 1. So that's where that came from. And you can see in air, the speed is only slightly smaller. This number is only going to be slightly smaller than the speed of light in a vacuum. So in air, it's still pretty close to a vacuum. But then for a diamond, it's traveling a lot slower. Light is traveling a lot slower in a diamond than it is in a vacuum. Anyway, I'll leave you there. We're going to do that in a couple of more videos. We're going to do more examples.
All right, that was a very advanced physics lesson. If you ever take physics, you're going to have to be able to calculate all of that. And in that picture, sometimes if you ever watch the videos where they're trying to catch a fish and they have to spear the fish in the water is a certain medium, and where you see the fish or where the spear is going to go is two different places. So it's because you're in the air and then the fish is in the water, so the light bends, like how the straw looks like it's in a different place in the glass. And that's because of visually the light bends. All right. So like I said, that was a very deep physics lesson, and trust me, you won't need all of that, but that was just something they included in the module, so you should watch it. All right. But it all has to do with the light bending, this polarizing light. Okay. And you have a polarizing microscope that does that. And so a lot of times they look at specimens that they might be in an oil suspension, a water drop suspension. So the light is going to bend. Okay. So they're giving you different pictures here, examples that you would see under a polarized microscope. All right. Moving on. Okay. A microspectrophotometer. Isn't that a tongue twister? And they break it down for you right here. So micro, obviously meaning very small. Spectro has the range of colors being formed by white light. So you all understand, like if you've ever seen the light go through a prism, it goes in as white light, and the prism, as it goes through the glass, breaks it up into the colors of the rainbow. Okay, so that's the spectrum. When we say spectrum, we mean the range of different colors. Photos for light, and meter, the object is being measured. So it is measuring light and the colors that are going through on very small things. Alrighty. So take a minute to read through this, and then let's look at exactly, like I said, the whole point was to get to how are we using this in forensics. So take a minute to read this paragraph. I'm not going to read it to you, but and all that conversation that he was going through about wavelengths and light traveling through different mediums. And again, he used terms like medium. So understand, air is a medium, water is a medium, oil would be a medium. Those are different things that the light will pass through is a medium. Okay. He also said a vacuum, and we don't mean a vacuum cleaner. We mean a space that has no air in it. So if there's no air in it, there's nothing to diffract, which bend the light. So that's what we mean by a vacuum, where they've taken all the air out. There's nothing to disturb the matter as it travels through that object. Okay, so again, take a minute to read that paragraph, and then we want to look at analysis of trace evidence. So coming back up here, what we're going to use this microscope for is it combines the function of a microscope with the function of a spectrometer, which means it's going to analyze the different colors. So like it says here, it might be important to say, to get the exact shade of a paint, to know where it came from, this car or that wall or another wall. This is what you would use this microscope for. All right, so this is the important part. It is often used in forensics for trace evidence analysis. And what are we analyzing? Paint fibers, hair fibers, drugs, different types of drugs. And later on, when we look at that, we're going to learn that we're going to actually do drug testing, and they give you different colors based on the type of drug. When we get to it, it's a whole list of drugs you'll have to know and how to detect them. Okay, biological evidence, blood, sperm, secretions, saliva. All right, uh, glass from a car, window, person's glasses, um, all those types of um, evidence. All right, we're going to determine the evidence and document have qualities of fluorescence. That means they glow in the dark, to help identify them and match them to other samples. Plastics, they can use this machine to match the, and when they say fingerprints, they don't really necessarily mean a fingerprint, in that each object has a certain pattern to it, and which would be like a fingerprint. It's unique to that type of plastic or object. And then gemstones, they can use the microscope to identify the colors in gemstones. Alrighty, and again, that pretty much said what that says up there. Alrighty, scanning microscope. Take a minute to read this over, and I'm gonna stop sharing for a moment. Um, we're gonna look at one more video on how they examine bullets for evidence. So read this one over. Be right back. All right, these are not cooperating today. Not to mention most of these are not approved by Muskogee County. Okay, we're not gonna do that. All right. If you finish reading that section, do click on all of the parts. Again, those are the parts of the microscope that you kind of did in the, except in scanning electron microscopes, they're a little bit different. So click on each of those headings and read what it says for each part. Sample chamber, detectors, and again, the vacuum chamber. So an electron microscope is not something that you would have in a classroom. They have those in big science labs, big forensics labs. This is not the microscope that you would have in anybody's school. All right. And then get to the module wrap up. All right. So we will probably deal with the module wrap up next week because I don't know. Are any of y'all 10th graders? Because tomorrow they have the PSAT. Some people might be missing. Any 10th graders? Just kind of raise your hand to no. Okay, so that means we'll have regular class. Won't be nobody will be missing. Good, good, good. All right, but we're going to do an activity tomorrow, and we'll worry about this module wrap up. But do look at the module wrap up. Look at the microscope review. Make sure you have turned in. Let me check. Gradebook should have it by now. So we are starting fresh. The only thing, and see, I'm looking at this now, like about 10 of y'all have not turned that in. All right, so the microscope is due today. So let me stop talking and make sure that you get that turned in. It is due today. Today. Let me change that date. And again, what I am doing this quarter is I am going to put available date, but I'm put the available date for a month. So if you can't get the work in a month's time, then I'm not looking at it anymore. So the nonsense that we went through at the end of last quarter with people trying to do things at the last minute and saying, please open that for me. If you haven't done it in a month's time, that's a zero. It's still going to be a due date. I still don't want to be looking at old work for weeks and weeks and weeks. So this is still going to be due. I'm gonna put this because of the break. I'm gonna make it due next week. But this was open on the 2nd, and so by now you should have had it finished. Okay, so that's just a heads up, folks. I am not going to be looking at late work forever. I would rather you do it late than get a zero, but there is a deadline to everything, so you need to start adhering to deadlines. All right, so let me change the due date on this. But like I said, I'm looking at the grade book. This is the first grade for this 9 weeks, and I'm looking like 9 of y'all haven't done it yet. Okay, all right. And that's only so that zeros don't start popping up. And I got a lot of emails, people worried about getting a zero. You don't have a zero because it just was due today. All right. All right, so we got a few minutes left. So finish reading, look at the module wrap up, get that microscope activity submitted. Yeah, about 5 minutes left to class. So let's handle that. There was, let me go back and see if I did. There was a score on that where you did the quiz at the end. So hopefully, and I didn't put that in the instructions, but I did kind of want you to screenshot your score. But since I didn't put it in the instructions, we'll leave that alone this time. This time. Here's There's no tutorial this week, but tutorials will start back up next week. And again, with tutorials, you don't have to sign up. I am in the Zoom and you just show up. It'd be nice to let me know that you're coming, but just show up. It's not on appointment basis. I will be there. All right, those of you who have already turned in your worksheets, you're good to go. If you have not turned in your worksheet, you got 2 more minutes. So you hang around, turn in your worksheet. Those of you who have turned them in, have a good day. Have a good day. If you haven't turned it in, just hang around. Stay a minute. Figure out why you haven't turned it in.